Okay, today's lesson is on moments, and we're going to start with a starter here, looking back to last lesson, which was looking at momentum. So pause the video and have a go at the question. Okay, so we've got a bus of 1,000 kilograms travelling at 10 metres per second. It comes to a complete stop in a time of 20 seconds. How much braking force is applied? So we're using the equation from last lesson, force equals change of momentum divided by time taken. And our change of momentum, well, our start momentum is 1,000 times 10, and our end momentum is 0. So 1,000 times 10 minus 0, divided by our time, which is 20 seconds. So 10,000 divided by 20, which gives us a force of 500 newtons. Okay, now we're moving on to look at moments, and it's really important that you don't confuse moments with momentum. A moment is the turning effect of a force, and that's equal to the force times the perpendicular distance between the force and the pivot. Moments are measured in Newton meters because they're force in newtons times distance in meters. Okay, we look at them in terms of things balancing. So I've got a pivot with a board on top of it, and I've got a 5 Newton force on one end, and we're going to say that's 2 meters from the pivot. So the moment is going to be 5 times 2, which is 10 Newton meters. And as I said before, I mentioned that it was perpendicular distance. Those two things need to be at right angles to each other. That's really important. Okay, have a go at these questions. Pause the video for a moment while you do that, and then we'll go through them. So question 1 asks, what is the moment when 30 newtons is applied 2 meters from the pivot? So to answer that, we need to do 30 times 2, which of course gives us 60 Newton meters. Number 2, what is the moment when 15 newtons is applied 0.5 meters from a pivot? 15 times 0.5 is 7.5 Newton meters. Now for question 3, we're after the force. What force causes a moment of 20 Newton meters when applied 4 meters from a pivot? So in this case, we're doing 20 divided by 4, which gives us a force of 5 newtons. Question 4 again is after the force. What force causes a moment of 50 Newton meters when applied 0.5 meters from the pivot? 50 divided by 0.5 gives us 100 newtons. And then finally, we're after the distance from the pivot for a 2 Newton force to create a moment of 100 Newton meters. So we need to do 100 divided by 2, which is 50 meters. Okay, so the last bit of information here is something called the principle of moments. And the principle of moments tells us that if an object is going to be balanced, then the sum of the clockwise moments acting on that object needs to be equal to the sum of the anti-clockwise moments. Okay, so I've put a little reminder up on there for you to show which way clockwise and anti-clockwise is, but just think of which way the clock goes round. Right, so let's have a look at this in practice. If we've got a board on a pivot, and then say I've got 5 newtons on one side, and that is 2 meters away from the pivot. Okay, now that is going to be creating a clockwise moment because it's going down on the right hand side. We've got a mystery force on the left hand side that's 1 meter away from the pivot, and that's going to be creating our anti-clockwise moment because it's going down on the left hand side. So our clockwise moment is going to be 2 times 5, which is 10 Newton meters. Our anti-clockwise moment, because of this principle of moments, we can see from the diagram that it's balanced. So that tells us that that's also got to be 10 Newton meters. Otherwise, it wouldn't be balanced. It would topple to one side. Okay, so if we know that the overall anti-clockwise moment is 10 Newton meters, then we can work out what the force is as the anti-clockwise moment divided by the distance. So in this case, that's going to be 10 divided by 1, which is 10 newtons. Okay, now I've got a little experiment for you to have a look at. Okay, so in this experiment, what I'm going to do is just demonstrate the principle of moments and the idea of clockwise and anti-clockwise moments in moments balancing. So we've got a little wooden pivot here with a piece of wood over the top of them. Now that should be balanced by itself, but someone's taken a little bit of wood out the end of it, so it doesn't quite balance, but it's close enough to be good enough for our needs. Now I'm going to start by putting 1 Newton at a distance of 25 centimetres from the pivot. Okay, so that goes on like so. And what we're going to do is we're going to take 2 Newtons on the other side and see at what distance from the pivot that starts to balance, or rather at what distance it tips onto the other side. So if I start near to the centre and I gradually push that out, it eventually reaches a point at which it tips. And if I measure that distance, that is at about 12.5 centimetres. So you can see there that we've got 2 times 12.5 being equal to 1 times 25, which is what we would expect to happen. We can also look at what happens if we've got multiple weights on the same side and how we balance that. So if I take these two and I put them on this side, if I put them 10 centimetres away from the pivot, so we've now got the 0.25 Newton meters from this one, and we've got 0.2 Newton meters from this one. So that gives us 0.45, and we would expect therefore that to be balanced by a 0.45 Newton meter on the other side. So I'm going to take 3 Newtons. Now 0.45 divided by 3 is 0.15. So if I put this at 15 centimeters from the pivot, it should balance. So I've just put that in at 14 centimeters. I'm just going to move that along. You can see it just coming to the balance point. Oh yeah, that's gone. Oh, not quite. And there we go. And that's happened at 15.5 centimetres, and that would be partly because of the fact that we've not quite got a symmetrical piece of wood, and the centre of mass of the weights isn't quite at the centre point. Okay, have a go at the questions that I've put on Fronter.